Imagine a world where buildings never need repair, because they possess the power of biological healing. We are currently reverse engineering a 2,000-year-old secret that modern engineering simply cannot replicate. If we can't decode this ancient maritime mystery, our contemporary cities are destined to fail, while the past remains standing. It is not a metaphor. It is not science fiction. It is a documented, peer-reviewed, laboratory-confirmed reality. Ancient Roman concrete, made without a single piece of steel, without computer modeling, without modern chemistry, heals its own cracks. And we have spent decades trying to understand how. Until now. Welcome to Haunting Mysteries. Let us dive into the forgotten Roman concrete formula. The 2,000-year-old self-healing technology scientists finally decoded. Here's the scale of the problem we are facing right now. The United States alone spends over $125 billion every single year repairing concrete infrastructure. Bridges, highways, tunnels, seawalls, ports, buildings, cracking, crumbling, corroding. Modern concrete, the material that holds our cities together, has an average lifespan of between 50 and 100 years. Many structures don't even reach that. Salt water eats it from the outside. Steel reinforcement bars rust and expand from the inside, forcing the concrete apart in a slow-motion structural explosion that engineers call spalling. We are pouring billions into repairs. We are rebuilding structures that will need to be rebuilt again in another generation. And then again after that. It is an endless, expensive, and deeply unsustainable cycle. And here is the haunting part. While we are spending those billions, the Pantheon in Rome is standing perfectly, 2,000 years old. The world's largest unreinforced concrete dome. No cracks requiring repair, no steel rebar rusting inside it, no structural intervention needed. Ancient Roman aqueducts, built before the birth of Christ, are still carrying water in parts of the Mediterranean today. Roman harbor walls, submerged in the sea for 2 millennia, are not crumbling. They are strengthening. The Romans had something we lost, and science has only just figured out what it was. To understand just how remarkable Roman concrete was, you first need to understand what the Romans built with it. The Pantheon, completed in approximately 125 AD under the Emperor Hadrian. Its dome, made entirely of unreinforced concrete, spans 43.3 meters in diameter. That is wider than the dome of St. Peter's Basilica, wider than the dome of St. Paul's Cathedral in London. And it has not moved. It has not cracked through its structural core. It has not required the kind of major intervention that would be necessary if any modern building of equivalent scale were left alone for 2,000 years. Then there are the aqueducts. Rome had 11 major aqueducts supplying water to the city and its surrounding regions. Many were built partly or wholly from concrete, sealed with a hydraulic mortar so impermeable that it could hold water for centuries without leaking. And then there are the maritime structures. The Romans built harbors and breakwaters using concrete that was literally cast into the sea. Submerged, surrounded by salt water, subjected to constant wave action, tidal pressure, and the slow corrosive chemistry of the ocean. And those structures are still largely intact, not just surviving. In many cases, they are measurably denser and stronger than the day they were built. The ocean, the thing that destroys modern concrete fastest, was making Roman concrete stronger. How? That is the question that has consumed researchers for generations. The Roman concrete formula, known as opus caementicium, was not a closely guarded secret in its time. Roman architects and engineers wrote about it. Vitruvius, writing in the 1st century BC, described the ingredients and the process in his architectural treatise De Architectura. The basic recipe was this: volcanic ash, specifically a fine, gray ash from the region around Pozzolana on the Bay of Naples, known today as Pozzolana. This ash was so important to Roman construction that it was transported across the entire empire by ship. Lime, calcium oxide, produced by burning limestone at high temperatures. Seawater are fresh water, and aggregate, rubble, rocks, and broken pottery. Mixed together, these ingredients produced a concrete that set hard and gained strength over time. For centuries, scientists assumed the volcanic ash was the primary reason for Roman concrete's durability. And they were partly right. But they were missing something. Something that sat in plain sight, literally visible to the naked eye in cross-sections of ancient Roman concrete for decades. White chunks, scattered through the gray matrix of the concrete like chips of paint. For years, researchers dismissed them as evidence of poor mixing, sloppy workmanship. Incomplete incorporation of the lime. They were not sloppy workmanship. They were the secret.
This ancient Roman concrete holds the secret. Its self-healing properties lie within these lime clasts.
In January 2023, a team of researchers led by Admir Mosik of MIT published a study in the journal Science Advances that changed everything we thought we knew about Roman concrete. They had been studying 2,000-year-old concrete samples from the ancient city of Privernum, near Rome. And they focused on those white chunks, those lime clasts that everyone had assumed were a sign of careless mixing. Using advanced microscopic analysis, they discovered that these clasts were not mistakes. They were a feature. When cracks form in Roman concrete, as cracks inevitably do in any material over 2 millennia, water seeps in. And when water seeps in, it dissolves calcium-rich material from those lime clasts. That dissolved calcium then recrystallizes, forming calcium carbonate, and physically seals the crack. The crack heals, not partially, not cosmetically. The crack is chemically bridged, structurally sealed, and effectively erased. To test this, the MIT team created 2 sets of concrete, one using the Roman hot mixing method with lime clasts, one using a standard modern formula without. They cracked both samples deliberately, then ran water over them. 2 weeks later, the Roman-inspired concrete had completely sealed its cracks. The modern concrete had not sealed at all. 2,000 years ago, the Romans had engineered a self-healing material. And we had dismissed the evidence as incompetence for decades. So how did the lime clasts get there in the first place? And why doesn't modern concrete have them? The answer lies in a process the MIT team calls hot mixing. And it turns out to be the single most important thing the Romans did differently. Modern concrete production mixes cement with water first, a process called wet slacking. The lime is fully dissolved before it ever contacts the aggregate or the other dry ingredients. The chemical reaction is completed early, before the concrete is ever poured. The Romans did it differently. They mixed quicklime, calcium oxide, directly with the dry volcanic ash and aggregate, before adding water. When water is finally added to this dry mix, the quicklime reacts violently and exothermically. It generates intense heat. And this is the critical moment. The heat drives chemical reactions that cannot occur at room temperature. Compounds form that would never form in cold mixing. And crucially, some of the quicklime reacts incompletely, leaving behind those reactive white chunks. The lime clasts, preserved, distributed throughout the concrete matrix, waiting for the day, decades or centuries later, when a crack forms and water seeps in. And then they activate, and the concrete heals itself. The hot mixing process also dramatically accelerated curing time, which meant the Romans could build faster than cold mixing methods would allow. Speed and longevity, in a single technique. It was not accidental. The Romans understood what they were doing, even if they could not describe the chemistry in modern terms. The self-healing lime clasts explain why Roman concrete survives on land. But they don't fully explain the maritime mystery, why Roman harbor walls became stronger after centuries in the sea. For that, we need to talk about a mineral called Aluminous tobermorite. When the volcanic ash in Roman concrete, that Pozzolana from Pozzolana, comes into contact with seawater, a slow chemical reaction begins. Over decades and centuries, the minerals in the ash react with the calcium in the concrete and the aluminium and silica in the seawater, to form interlocking crystals of aluminous tobermorite. This mineral is extraordinarily rare in nature. It is extremely difficult to synthesize in a laboratory. And it is, when it forms, one of the most structurally robust minerals known to materials science. It grows between the existing crystals of the concrete, reinforcing them, filling the microscopic gaps, binding the structure together at a molecular level. The ocean was not attacking Roman concrete. The ocean was finishing what the Romans started. The longer those harbor walls sat in seawater, the more aluminous tobermorite formed inside them, and the stronger they became. Modern concrete, by contrast, is steadily destroyed by seawater. Salt penetrates the surface, reaches the steel reinforcement, and the rusting process begins. Within decades, the structure is compromised. Two materials, two completely opposite responses to the same environment. One of them was invented 2,000 years ago, and we are still struggling to match it.
Why we failed, the Portland cement story. So if Roman concrete was so clearly superior, why did we abandon it? The answer, as with most things in history, comes down to economics and speed. In 1824, a British bricklayer named Joseph Aspdin invented Portland cement. It was cheaper to produce than volcanic ash concrete. It was faster to set. It was consistent, you could manufacture it in industrial quantities with predictable, standardized results. And it was strong enough. Strong enough, in the short term. The 19th and 20th centuries demanded speed. Industrialization demanded it. 2 world wars demanded it. The post-war construction boom demanded it. Portland cement, mixed with steel reinforcement to compensate for its brittleness, could build faster and cheaper than any previous method. And so the world switched. We built roads. We built bridges. We built skyscrapers, dams, tunnels, and entire cities out of steel-reinforced Portland cement concrete. And for decades, it looked like the right decision. Then the steel started to rust. Here is the fatal flaw of reinforced concrete. Steel expands as it corrodes. When the rebar inside a concrete structure rusts, it grows. And as it grows, it pushes outward against the concrete surrounding it, forcing cracks to form from the inside. Those cracks let in more water, more oxygen, the corrosion accelerates, the cracks widen, and eventually, the concrete fails from within. Roman concrete has no steel. It has no rebar. It has no internal enemy silently tearing it apart. It simply ages. And as it ages, it heals.
Can we recreate it, the future of ancient concrete? So can we do it? Can we recreate what the Romans made? The honest answer is, we are getting closer. But we are not there yet. The MIT research team, led by Admir Mosik, has already used the insights from their 2023 study to produce a Roman-inspired concrete in the laboratory. A concrete that incorporates hot mixed lime clasts. A concrete that, in testing, successfully seals its own cracks within weeks of fracture. But scaling this from a laboratory sample to a construction-grade material is an enormous engineering challenge. The Pozzolana volcanic ash that the Romans used is not available everywhere. Sourcing, processing, and distributing it globally would require new supply chains. Hot mixing generates more greenhouse gas emissions in the short term than Portland cement production, though researchers argue that over a full structural lifetime, Roman-inspired concrete wins decisively on environmental impact because it never needs to be replaced. There is also a question of compatibility. Our modern construction systems, the formwork, the pumping equipment, the reinforcement schedules, are all designed around Portland cement. Switching to a fundamentally different material would require retraining, redesigning, and re-engineering entire industries. But the direction is clear. For long-lived infrastructure, seawalls, harbor installations, bridge foundations, water treatment systems, Roman-inspired concrete may be the most durable, most sustainable, and ultimately most cost-effective choice humanity has. The Romans built for millennia. Perhaps it is time we learn to do the same. Final verdict: the Pantheon is older than Christianity. It was standing before the fall of the Western Roman Empire, before the Dark Ages, before the Renaissance, before the Industrial Revolution, before every skyscraper ever built, and it will almost certainly still be standing when many of those skyscrapers are rubble. We are so accustomed to thinking of progress as a straight line, always forward, always better, that we forget how much knowledge can be lost in the gaps between civilizations. The Romans did not know about atoms. They did not know about pH levels or calcium carbonate crystallization or aluminous tobermorite mineralization. But they observed, they experimented, they refined, and they produced something that 2 millennia of chemistry, engineering, and material science is only just beginning to fully explain. The most humbling thing about Roman concrete is not that it lasts. It is that it improves. It gets better with age. It heals. It adapts. While we spend hundreds of billions repairing what we built just 50 years ago. If that is not an argument for looking backwards before we build forwards, I don't know what is. If this video made you see the ancient world differently, please give it a thumbs up. It genuinely helps more people find this content. Subscribe, hit the bell, and leave me a comment. What other ancient technology do you think we have lost and should be trying to recover? I'll see you in the next one.